As it turns out, one-of-one functions are the only functions that have a well-defined inverse. Let's go ahead and define the inverse of a function, and we'll see why this is true. Suppose first that f is 1 to 1, and let's go ahead and call the domain A and the range B. The inverse of f, written as f raised to the negative 1, then has a domain B and a range A, and is defined as follows. F inverse of y is going to be equal to A. This only occurs if and only if f of x is equal to y. Let's look at a simple example of why we need this condition to be 1 to 1. Suppose we had a function then whose domain was given by the following and whose range is given by the following, which isn't 1 to 1. Let's go ahead and try to define the inverse of this given function here, which we'll call f. In this case, the domain of f inverse is going to be given by d and e, and the range of f inverse is going to be given by a, b, and c. Here we have d would go to a, and then we'd have e would go to b, and then e would also go to c. But here's exactly where we have the problem. Remember the definition of a function. We can only assign one output for every input, and here we have an input being assigned to two different outputs, and so this inverse is not a function. This is the exact reason why we need our functions to be 1 to 1 if we want to define an inverse. Otherwise, the inverse is not going to be a function. Let's go ahead and reiterate this definition by looking at a problem. In this problem, we're given the evaluation of the function f for f of 1 is equal to 3, f of 2 is equal to 0, and f of 6 is equal to 8. And what we want to find is the evaluation of f inverse at 3, f inverse at 0, and f inverse at 8. By definition, what we need to look at this again is that f inverse of y is equal to x only occurs if and only if f of x is equal to y. Then f inverse evaluated at 3 is going to be equal to 1 by this definition. Also, f inverse evaluated at 0 has to be equal to 2 by this definition. And finally, f inverse of 8 by this definition is going to be equal to 6. And so this is going to be our solution. One of the main reasons we're looking at inverse functions is because an inverse function undoes the original function. And let's just go ahead and state the following theorem that will describe this behavior. So this theorem is called the inverse function property. Let me go ahead and write the conditions down for this theorem, and then we'll go ahead and describe what's going on. Okay, so the one condition that we need for the inverse function theorem is that f has to be a 1 to 1 function. Let's just go ahead and call the domain A and the range B. Now, the inverse function f inverse satisfies the two following properties. Number one, we have that f inverse composed with f of x is going to be equal to x for all x in the domain of our function x. And the second thing, f composed with f inverse is also going to be equal to x for all x in the domain of our inverse function b. Furthermore, we can make one more statement. Any function, let's call it g, satisfying 1 and 2, is in fact an inverse of f. So we'll be using this inverse function property throughout the next section, but let's just go ahead and apply it to the next problem. Show f of x is equal to x squared, where x is greater than or equal to 0, is the inverse of the given function, which is going to be the square root function. So the thing that we need to do is we need to go ahead and show that f composed of g is equal to x and g composed of f is also equal to x, because then by the last part of the inverse function property, this tells us that f is going to be equal to g inverse. Number one, again, f composed of g of x is going to be equal to the following. Square root of x squared, which is equal to x. And if we do the same thing the other way, so we're composing g with f, this is going to be equal to the square root of x squared, which is again equal to x. So by the inverse function property again, this implies that f is going to be equal to g inverse.